Can you see my screen؟ میشه چک کنید که اسلاید من میبینید؟ Okay, good. Good morning, everybody from New York. I know it's almost evening in Iran, so good evening to you, everybody. My name is Dr. Puya Ghazizadeh. I am an assistant professor of computer science at St. John's University, and it's my pleasure to be here. First of all, I'd like to thank the organizing committee for inviting me and also creating this opportunity for me and others to share their research and findings with, uh, with you guys. And also, I'd like to thank you for taking time, the audience, for taking time and attending this presentation. I would like to also make sure that everyone can see my screen because I will use the full screen mode, so I won't be able to see the chat box. Okay, so a little bit about my background. So as I mentioned, I'm assistant professor of computer science at St. John's University in New York. I received my PhD in 2014 from Old Dominion University in Norfolk, Virginia. And the last year of my PhD program, I was also adjunct professor at Old Dominion University. And after graduation, because I always had passion for research and teaching, I joined academia. I became assistant professor at Millersville University in 2014, right after my graduation. And then after 3 years, I joined Seton University in New Jersey. And eventually in 2020, I joined St. John's University in New York City, and I've been working there for more than 4 years. I have been involved with different conferences. Currently, I'm serving as associate editor for ITS C, which is Intelligent Transportation System Conference, and also I'm serving as associate editor for Intelligent Vehicle Symposium, and I'm part of committee members for different conferences. I've been a reviewer for ITS transaction, IEEE ITS transaction for a while, and I have some other research activities that basically are aligned with my research topic. I've been doing research in different areas. My main research is vehicular cloud computing that I'm going to share with you. I also have done research in security and privacy in outsourced database. And also I've been working with aerospace department, and we have published papers regarding airline design. And I'm also involved with IoT conferences. So this is just a summary of my research activity. I have published more than 30 papers in different journals and conferences. So let's talk about the origin of Vehicular Cloud. We introduced this concept. This was a new concept that we introduced for the first time in 2014 at Old Dominion University at our research group. And my thesis was the first thesis that is related to Vehicular Cloud. And the title of my thesis is Resource Allocation in Vehicular Cloud. My focus was mainly on static Vehicular Cloud, and we have continued this research since 2010. And we have worked on different aspects of Vehicular Cloud because this was a new technology. So there are many challenges that should be addressed. and we have tried to address some of these challenges. It's an ongoing effort, so because as I mentioned, it's a new technology, so you have to make sure you address all the challenges. Um, so this is just mm, an origin of Vehicular Cloud. Also, I'm teaching a course. It's a topic course, and I have designed this course. It's based on my research, and it's called Vehicular Cloud Computing. I offered this course in 3 different universities, and it has been a very popular course. Okay, so that was just a brief introduction about myself and my research. Our focus today will be Vehicular Cloud and specifically uh, fault tolerance. If I want to give you a very short description about Vehicular Cloud, this is the line that I can use. If you have never heard about this concept, basically uh, we use modern vehicles in order to provide computation services. So this is a very short description for you, so you know what we are gonna see in the next few slides. Vehicular Cloud has two main components: cloud computing and uh, vehicular network, or specifically vehicular attack network. All of you are familiar with cloud computing, and this is a very flexible service where you can get different computation services almost available everywhere as long as you have access to internet. And this was not the case before cloud computing. In the past, you had to have your own infrastructure if you wanted to provide a specific computation service. But after the cloud computing, this changed and it became very popular quickly. And also, this type of service will help with cost reduction because you don't need to maintain your infrastructure. You just pay basically for the service, and you can easily scale up or scale down your services based on the number of users that you have. Let me see. Okay, we can basically divide cloud uh, into different tabs in terms of service. Of course, there are different classifications. This is the basic one. So we have software as a service, we have platform as a service, and we have infrastructure as a service. In software as a service, this is a typical example. This is the typical service that everyone almost uses this service. For example, if you have Google Drive, that is an example of software as a service. Google Calendar uh, and Google Talk also are some other examples. For platform as a service, this is where Google basically the example is Google's app engine. This is for developers when they want to experience distributed environments. When they develop their applications, they need to get access to this type of environment. This is provided by uh, cloud services such as Google, and this is called platform as a service. And the next one is infrastructure as a service. This is where you get the hardware, and then you have to set up and configure the system yourself. This is usually for uh, computer scientists because they should have the knowledge in order to set up and configure the environment. There is another type of classification for cloud. We have public cloud, private, and hybrid. Uh, in public cloud, and the owner is the provider, so the user doesn't own the uh, cloud. This is again, this can be Amazon services or cloud services. Private cloud is where the user owns the infrastructure. This is very typical for financial institutions because they have sensitive data, so they want to be able to control the data and all kinds of access to the data. So this can be an example of private cloud. And then we have hybrid cloud, which is combination between uh, private and public. Uh, Google and Amazon, they have this kind of hybrid clouds, and on the private cloud, they will basically develop their applications, and when it's time to release it, they use the public cloud so everyone can get access to it. Okay, so let's move on to the next slide. Virtualization is one of the main elements of cloud computing and vehicular cloud. Uh, Most of you are familiar with this technique. Basically, this creates a layer between the hardware and operating system, and you can provide isolated environment in terms of computation, and you can basically provide different resources such as CPU, storage, and network. When it comes to vehicular cloud, containers are also they are essential part of this cyber physical system, and containers make the job even easier because once you have container engine installed on the operating system, you can load different images, and usually they are lightweight, so this will not create overload on the system, and it's very suitable for vehicular cloud. Um, in terms of the direct relation between vehicular cloud and containers, um, we can assume that uh, cars and vehicles that are involved in vehicular cloud, they have uh, installed the container engine ahead of time, so it's already preloaded, and the OS as well. And regarding the image of the container, they can also preload that, or they can download the image when they join the vehicular cloud. So we talked about the first main element, which is cloud computing. Now I want to talk about vehicular ad hoc network, or VANET. VANET uh, uh, is a network of cars that are connected. This is different from wireless nodes because VANET has its own communication device, and VANET is used in order to complement the existing infrastructure. This is an example of VANET. So cars that have the communication device can send messages to each other. For example, if there is an accident at specific intersection and there is a need for uh, there is a need for hospital or any emergency service, uh, the car that is at that intersection can send the message to the next car and then to the infrastructure. So they will let they will let the authorities know that there is a need for a specific type of service, health service, or other services. And of course, this will help the people involved in the accident. VANET has been around for more than 20 years, and let's see what was the motivation behind VANET. The main one was detecting highway incidents. So uh, accidents are the issues everywhere, not only a specific country. Everywhere in the world, there is always issues with accidents. So we are trying to reduce the. So this is one of the main elements or motivations behind VANET. The other one was uh, basically the cost that is related to congested highways and also fuel waste. So while you are sitting in the traffic, you are wasting time. Probably know better. You know this. You are familiar with this concept. If you are in a heavy traffic, basically you have to wait there for a couple of hours sometimes, and then that means you're not gonna get anything done. You're gonna be late for your work or uh, other things. So that impact the productivity. At the same time, the engine is on and running, so the fuel is wasting. So based on the calculation that um, have been done in this area, U.S. basically loses more than $80 billion per year. This was like a couple of years ago. Probably it's more than this right now. The other concept related to VANET is the communication device. So there is the communication device called dedicated short range uh, communication, and this is like a radio that is installed in the cars, and that's how they can communicate and send each other a message. U.S. Federal Communication Commission has allocated specific spectrum for DSRC, and it's reserved for that purpose. And the range of communication for this device is 1000 meter. Uh, we have different types of communication in VANET. We have vehicle to vehicle communication where two cars can talk to each other, and we also have vehicular to infrastructure where vehicles can talk to the infrastructures on the road. VANET has two main applications, safety and commercial. As I mentioned, it can be used in order to detect accidents. So once the car detects the accident, the car can send message to the car behind it to slow down so it doesn't create more accidents. So this is the safety application. And the commercial one is where you have um, areas and you broadcast the information regarding gas station and food stations and travel stations. Okay, so far we talked about cloud computing, we talked about VANET, so we discussed these two main components. We are getting closer to the vehicular cloud concept, but before that, I have to talk about modern vehicles. Uh, Modern vehicles are equipped with sensors. Um, average um, Average modern car has 100 sensors, and this number is growing. It's going towards 200. And when you have sensors, that means you are gathering data. And since you're gathering data, there should be a processor in order to process the data and use that in order to navigate. Um, as you see, it turns out modern cars process more than 4,000 gigabytes data per day, and this number is old. It's a couple of years old. Uh, by now, it's more than this. So when you have this amount of data to be processed in order to make decisions regarding navigation, that means there should be a processor, a very powerful processor on board. So basically, modern vehicles have a very powerful processor on board. It's almost it's more than 150 MacBooks. This is again a number from a couple of years ago. And once you have this powerful computation power, um, you have to use it. And this is the whole idea behind vehicular cloud computing. An interesting news here. So with this powerful computation power, even Lamborghini can basically activate drifting feature in the car, which is something that professional drivers do. So this is interesting. So let me summarize. So basically, uh, because of the modern vehicles that have very powerful computation power, we have resources that we can use, and this is the motivation behind creating Vehicular Cloud. Uh, that means you are gonna have a network of cars with very powerful computation resource, and they can create a cloud, they can create a network and provide uh, different services. We have two different types of uh, vehicular clouds. We have static and we have dynamic. Static is a typical airport parking lot. Usually, um, airport parking lot is always packed, and people leave their cars there for a couple of days. And imagine you have a parking lot full with uh, computation nodes, and they are left there for a couple of days. The idea is to use them in order to provide computation power. So this is the um, static vehicular cloud. Of course, you can extend this idea to uh, university campuses or mall parking lots and or any other parking lots where you have um, cars parked there for a couple of hours. Um, Once you have this model, then everything changes. First of all, you will be able to provide local services, um, local computation services uh, to the airport, mall, and university. And at the same time, people can basically have some kind of income by renting out their cars. Most of the people drive to work, so when you park your car at work for a couple of hours, you can rent your car to the Vehicular Cloud. They pay you some kind of incentives in forms of payments, or they can provide you uh, free parking lot, which is necessary in large cities, and this will help to basically turn a typical parking lot into a business model and helps with this issue as well. And this all is available because of resource sharing model where you rent out your car, you share your resource, and in return you receive some kind of payments or free parking lot. So that was a static model uh, where you have cars parked in a parking lot. The other model is the dynamic model. So this is if you take a look at the image right here, you have cars on highway that are moving, and you can use these cars to create uh, clusters of cars and create vehicular cloud. You will have a controller, vehicular cloud controller that is connected to the access points. Access points are basically the are installed as infrastructures uh, on the road, and you can see multiple access points for different reasons. We can use them in order to communicate with the cars, and but every access point has a specific range, which is specific coverage range, and this should be considered when we discuss different issues. So this is the dynamic model. You have access points located with certain distance and certain coverage, and you have cars on highway that are moving. In this model, the moment that the car joins the vehicular cloud, they will let the access point know about their exit, So because you have to know where they exit, so that's where uh, that- that's where uh, that you as a vehicle as a vehicle leave the cloud, and you basically lose access and connection to the access point. You may ask me, how do you do that? Let how do you let the AP know that you are living at this point? This can be done by using Google Map or other applications that you use for driving. So you have destination, and when you enter that destination, excuse me, when you enter your destination, by default, the application knows the map and the road, so it will help with the exit point, so it's obvious what is the exit point for the car. So this is the dynamic model. Now let's talk about some of the applications um, of Vehicular Clouds. We can talk about natural disasters. I know this is not very common in Iran, but in US there are different, so many natural disasters that we have in different states, uh, and managing them is essential. So once you have a cloud of the cars that are in the congested area, you can create a cloud service and help with managing the resources, including the traffic. So this will help to basically broadcast information about shelters and food stations and other things. So managing natural disaster is one of the examples. On the right side, you can see New York City during Hurricane Sandy. So during this time, the power was out for a couple of days, and people and the city had serious issues. And because everything needs power these days, every service or application that you use is somehow related to electricity. And when you have a cloud of cars that are running on the road, it can be used in order to help the city in these kind of situations. Okay, let's talk about the difference between cloud computing, traditional cloud, and Vehicular Cloud, specifically static cloud. So imagine that this is a parking lot, and you have different cars arriving and departing randomly, because in most of the cases you don't know when a car arrives and departs, so you don't have access. You don't have access to the schedule, or you don't have any control over them. This means cars that are your computation nodes can uh, arrive and depart randomly, which means you may lose your computation node uh, while you are in the middle of processing. So you don't have this issue in traditional cloud. Why? Because in traditional cloud, the servers are there, and um, there is no failure, or failure rate is very, very low. And you can basically assume that there is no failure. The nodes are there all the time. But in Vehicular Cloud, that's not the case. Nodes can arrive and depart randomly. And this creates a serious challenge for Vehicular Cloud, and we should be able to address this. This is the main focus of this uh, presentation. We are going to talk about how to address this issue in Vehicular Cloud. Besides the fault tolerance that I'm going to discuss in details, there are other aspects of Vehicular Cloud that I have been working on, like scheduling, completion time for both static and dynamic VC, communication protocol, and eventually security and privacy. Each of these topics are separate research by themselves, so we don't have time to get into details. I will just give you a short introduction about each one. But if you are interested, you can reach out to me later on and we can continue this offline. And the papers are out there, and you're welcome to study and review them. And if you have any questions, I'll be happy to answer. And this is, by the way, this is ongoing effort. So I'm still working on different aspects. Right now, my current focus is security and privacy. Um, so you are familiar with scheduling in computer science. It's a very famous problem in computer science, and there are different solutions for that. When we talk about scheduling, basically we have limited resources that we have to allocate to different jobs, and usually we have to optimize specific objective function. And this problem has been around forever in computer science, and we know that we have to basically define the objective function based on the problem. So scheduling is not a new uh, area for computer science, and again, there are so many different solutions for that. The one that I worked on early in this work many years ago was using linear programming, and also uh, I used genetic algorithms in other areas, uh, and they are good solutions. But for the environment that we have random arrivals and departures, they are not the most helpful solutions. That's why we used stochastic modeling, and we used different tools in order to overcome the challenge that we have in terms of random arrival and departures. Stochastic modeling is also something that we cannot cover in this lecture and presentation, but it's a very useful model, and I'm sure you can find resources out there to learn about this. Uh, so regarding linear programming, um, basically you have to use different constraints in order to define your problem and solve the constraint in order to get the solve the equation in terms of equality and inequality in order to maximize the objective function or optimize. Um, and genetic algorithm is basically based on using uh, crossover and mutation in order to create new solutions, and every generation we improve the solution until we get to the point that is good enough for us. And stochastic modeling is basically based on probability, where you have a model and the model has different states, and you have to determine the probability from moving one state to another state. And based on that, basically, uh, you will develop your analytical model. This is a result from one of our uh, papers a long time ago. This is based on linear programming. So you have the um, parking spots schedule and the cars that are available, and you also have the jobs in the system, and then you assign them to the different parking spots in order to optimize the objective function. As you see, the model, so the red spots that you see is the spots that we don't have any cars at that time. The white spots are basically the spots that we have cars there. So that means we have the computation node. So basically, you shouldn't allow a job to be assigned to red spots, and that's what the mm, program did. And if you take a look at this side, let me see if I can use my pen. So if you take a look at this job, so this is the number is the integer number is the ID for the job. So the model had to do some kind of migration to uh, migrate the job to this spot because of the limitations that we have. Of course, migrating has cost, so but apparently this was the uh, solution, optimized solution. Uh, Again, one of the areas that we covered in our research in the past was completion time. Uh, it's important for you to know when you finish the computation for a specific task because of the environment, which is different from traditional cloud. We have to figure out how long does it take for a typical job when we're using Vehicular Cloud. Otherwise, if you don't have the answer, then that means the customer most probably will not use this service if they are not sure how long does it take for a specific job to be completed. Um, we use two different strategies in order to complete the in order to calculate the completion time, J2 and J3. I'll discuss these strategies later on in the next slides. This is specifically for static. We have done the same thing for dynamic Vehicular Cloud, where you have different access points where you can download the job under one access point and upload the answer under the next one. Again, this will be a very uh, brief introduction. We don't have time to cover this, but it's good for you to know about these areas. So um, let's discuss the completion time for dynamic Vehicular Cloud. Once you have a car that arrives under the coverage area for AP, the car can download the task and the car can use the computation power in order to complete the task. At some point when the results are ready in the next part of the highway, the car can upload the results into the next access point. And we have developed an analytical model to predict this, so predict the completion time based on the different scenarios that we have. Uh, the other topic that we have covered in our research is communication protocol. Uh, when you have a dynamic Vehicular Cloud um, and you have coverage area, the access point sends out frame uh, frame structures to the vehicles, and vehicles should compete for this frame because of the limited bandwidth. So there will be some kind of competition between the cars under the coverage area, especially if you have many cars, if the highway is congested. So you have many cars in the coverage area that are competing for the frame that is sent by the access point. We have developed a specific communication protocol for this issue, and uh, we have different segments in our frame. Again, these are different uh, segments, and each one has different size, but the details cannot be covered right now. In this work, after we designed the communication protocol, we have also introduced two different betting policies, and that's how the cars can compete with each other in order to get the frame from access point. And each policy has specific performance based on the area and the coverage range, and the basically how congested is the highway based on the number of cars that we have on the highway. Uh, and eventually, security and privacy is the one that uh, I'm currently working on. So we have security and privacy issues in Vehicular Cloud, and this is not only for Vehicular Cloud. Any technology that you use out there, it has some kind of security and privacy challenges that should be addressed. And same thing for Vehicular Cloud, because cars can create a network, and because cars create a network and they communicate with each other, they can share different pieces of information, for example, location and other information, and this can be used by malicious entities to basically harm the node, and for that reason, we have to address this challenge as well. Of course, there are so many security and privacy solutions out there for different problems, but the traditional uh, approaches usually don't work or are not optimized for Vehicular Cloud. Why? Because Vehicular Cloud nature is different. In Vehicular Cloud, nodes move all the time, so they are highly mobile, and the topology is dynamic, it changes all the time, and also you can have different number of cars. At some point, this number can be very high. So because of all these characteristics, the traditional approaches usually don't work for VC. Um, we have used trust-based authentication methods in our work. This basically involves creating a cluster of cars, and in each cluster we have nodes that are overseers or observers. These nodes are certified by the access point, so they are trusted nodes. And in this type of authentication model, the previous activity and current behavior of the node and the feedback will be used in order to authenticate the node, if it's malicious or not. And there are different mechanisms that are used, like digital signature in the messages that are sent. Um, we presented two different approaches in different papers. Mm, the first approach is based on the typical approach where you use queries from the server. Basically, you're propagating queries, and this is done from the server side in order to authenticate the neighbors. Um, and then we presented another approach. This one is serverless, and of course, this is good because uh, this is not uh, uh, this does not create overload on the server because it's not relying on the server all the time to run and propagate different queries. And this is good news for Vehicular Cloud. Uh, okay, so these are all different topics, some of the topics that we have worked on in the past. And now I'm going to mainly discuss fault tolerance in Vehicular Cloud and the approach that we use. As I mentioned, the main issue here is random arrival and departure. Because of this, you may lose your resources and your uh, computation node, and that will create a failure in the system. When there is a failure, that means you're going to lose the computation, and that's not good because that's wasting the resource. So we have used stochastic modeling. The details of this model is in the papers. And if you want, you can review the papers. We don't have time to get into the details here. In our model, we have used checkpointing and redundancy mechanisms. These are mechanisms that are basically popular and have been around forever. Checkpointing is basically creating an image of the current computation in case the node left. You have this image to use to continue the computation. Of course, there are challenges with this process, and so many solutions have been offered. And the challenge here is what is the optimal checkpointing period? How often do you have to create the checkpoint? Because creating checkpoints is heavy and creates overload on the system, so you have to be aware of that. So there has been many solutions presented by different researchers, and but because of the nature of Vehicular Cloud, because we don't know the arrival time and departure time, usually those approaches don't work in our case. The other tool that we have used or mechanism that we have used is redundancy. Redundancy basically means to uh, assign a job to more than one node, more than one computation node. This creates some kind of um, backup that I will explain, but at the same time, um, you are going to use more resources, and you have to be also aware of that as well. Uh, as I mentioned, we have used stochastic modeling in order to create the analytical results. That's our prediction. Uh, and once you have the prediction, you can compare it to the simulation results and see how accurate is the model. Okay, here I'm gonna explain the model for you. Let me see if I can use, okay. So let's discuss this model. This is J2 strategy. J2 stands for job strategy 2. So here at the beginning, we have two cars, car A and car B, and we assign the job to both of these cars. So A and B are running the job at the same time. At some point here, car A decides to leave the vehicular cloud, the parking, which means uh, node A is not available anymore. What happens in this strategy is right there, node B will create uh, a checkpoint or an image from the computation, and once it's done, it will recruit another car named car C, and both car B and C will continue the execution. In our model, the assumption is we have enough cars in the parking lot, so the parking lot is full of cars. So once one car leaves, the other car, like car C, is available, so we can recruit car C and continue the execution. So at some point, so these two, car B and car C, continue the execution, and at some point here, car C decides to depart and leave, and immediately car B creates another checkpoint from the current computation, and once it's done, recruits another car called car D, and they both continue the execution. Uh, at some point, again, because these are all random arrivals and departures, so there is no specific pattern in the arrival or departure. And mm, At some point, car B uh, departs, leaves the cloud, the vehicular cloud, and car D creates a checkpoint, transfers the checkpoint to the new car that has been recruited, and they both continue the process until they finish the execution. So this is job strategy 2. Why it's called 2? Because we are assigning one task to two cars at the same time. Uh, this is the strategy, and we have developed the analytical model. There is an issue with this strategy. Usually, I ask the audience if you can tell me what is the challenge here, what is the issue with this model. But we don't have this option here to, so I'm going to explain it for you. This model has a failure point. Failure point is where the system fails and you lose the computation, and that is uh, happening right during the checkpointing. So if this is the case where car A already left and we have car B that is checkpoint, if car B leaves right during the checkpointing, then we lose all the computation. And imagine if it's here, when we are almost close to finish the task and the job, and then suddenly, because of the random departure, we lose all the computation. This is called failure in the system. So this is the answer. Basically, the failure in this model happens when the car leaves and departs during checkpointing process. So for that, you have to be aware of the failure point in your system. Once you have that, then you can anticipate, and also you can apply some mechanism in order to recover from that failure or avoid that failure. And we have done basically uh, we have created different scenarios, extensive simulations, uh, and at the same time we have created the uh, analytical model in order to predict that. So I'm gonna go ahead and explain the results for you. Uh, so let's talk about x-axis. X-axis is the average staying time or residency of the cars. So typical car can stay 3 hours for up to 8, and y-axis is the mean time to failure, basically the time in the system that the failure happens. Uh, for this scenario, we have used 10 minutes for the checkpoint duration. Of course, these are all parameters, and because we have the model, we can easily change the parameters and see all the results. And as you see, so let's pick one of the data points here. So this means if you have cars that are staying 3 hours in the parking lot by average, the failure point happens here, which is, I think, 30. So after 30 hours, you should expect to uh, have failure in your system. So you have to provide a specific mechanism in order to avoid that or recover from that. If you increase the residency time of the car to 4 hours, the failure uh, time also increases. So this is like 55. So if you have cars with uh, average residency time of 4 hours, then the failure happens in the system after 55 hours. And this is increasing, so uh, you can basically follow the same pattern here. If the residency time is 5 hours, then basically this will be the failure time. And of course, when the residency time is 8 hours, when the cars stay average 8 hours, then you have failure happening after 200 hours. And this is both analytical and simulation results. As you see, they match, and this confirms the basically accuracy of the analytical model, which is used for prediction. This is another set of results here. The difference here between this scenario and the previous scenario is the uh, duration for the checkpoint. Uh, so if the checkpoint, the previous one was 10 minutes, the checkpoint, this one is 20 minutes. So if uh, the checkpoint duration is 20 minutes and the residency time is 3 hours by average, then the failure happens at almost 19 after 19 hours, which is worse than this, and this can be justified because we increase the checkpoint duration, and if you have a longer duration, the probability of living during that increases, right? It's basically pretty straightforward, and this means that when you have longer checkpoints, then the failure happens faster compared to shorter checkpoints. Uh, and again, this uh, uh, the result is both simulation and analytical results, and they confirm each other, which means it shows the accuracy of the analytical model. Um, the other strategy that we have used and we have developed is J3. This is similar to the previous one. So if you understood the previous one, this is pretty easy. And J3 is job strategy 3, which means you know, we assign one job to 3 cars at the same time. So we have car A, B, and C in the parking lot, and we assign one job to all these 3 cars. They start to execute the job, and at some point, car A departs or uh, leaves the system, and car B immediately creates a checkpoint. Car C continues the execution. At some point, after the checkpoint, another car will be recruited. Again, we assume that we have enough cars in the parking lot, and they all continue the process and they continue the execution. At some point, uh, car D leaves, so car B creates the checkpoint. In the middle of that, car C also leaves. Once car B is done with the checkpoint, 2 more cars, E and F, will be recruited, and they continue the execution. And here, at this point, car B leaves, and again, car A will get a checkpoint, and so on. And at some point, they will be done with the execution. So this is similar to the J2, but of course the results are different. It's obvious from the results if you compare them with the previous results that failure point uh, in time to failure increases, and that's obvious because now you have 3 cars that are running. So this is almost 200. So if you compare this with here, the failure happened after 30, or yeah, after 30, uh, 35, and here happens after 200. 35 compared to 100. So after 200 hours, we expect to see failure in the system, and that's when we have to um, anticipate and we have to recover from that. So we have to apply some mechanisms in order to recover from that. Um, Again, the parameters that we have used here can be changed because we have the analytical model. You can just plug in the values, and we have printed both simulation results and analytical results, and the simulation results are also uh, printed here. Okay, so this concludes my presentation. Thank you very much for taking time and attending this presentation. I hope you liked it, and if you have any questions, I'll be happy to answer. I can see there is a link here for the questions. Let me see if I can open the link. I don't see the participants here. I just see the chat.
Yes. خب ببخشید صدای من الان؟
بله میشنوم.
سلام مجدد، خیلی ممنون از ارائهتون و یه سری بچه‌ها خوب یه سری سوالاتی رو پرسیدن که حالا من از شما میپرسم. بعد از این سوالات اگر حالا هر کدوم از دوستان تمایل داشتن که به صورت وایسی هم حالا سوال بپرسن، میتونن دستشون رو بالا بگیرن که حالا دسترسی بهشون داده بشه و سوال بپرسن. سوال اول در مورد اسکیلبیلیتی این مسئله است. حالا خب یکی از مواردی که حالا توی سیستم‌های دیستریبیوتد و حالا این روش vehicular cloud computing نسبت به cloud computing میتونه مزیتش باشه همین اسکیل شدن بهتر کل سیستم هست با توجه به تعداد بیشتر ماشین هایی که حالا وجود داره توی روش. گفته بودن که این رو هم یه بررسی بکنین که تا چه میزان اسکیلبل هست و این رو چجور میبینید اسکیلبیلیتی این روش.
خب این سوال خیلی خوبیه. ما باید ببینیم که داریم استاتیک کلاود در موردش حرف میزنیم یا داینامیک. اف کورس اگه داینامیک باشه یه کانسترین داریم که اونم coverage area of access point. خاطر اینکه این access point ها یه لیمیتی دارن واسه coverage area. به عنوان مثال ممکنه مثلا 20 تا ماشین تا 30 تا ماشین رو کاور کنن واسه یک کلاستر، سو اونو محدود میکنه. در مورد استاتیک کلاود خاطر اینکه ما خاطر اینکه کانکشن اونجا هست available، you can just plug in the car، فقط میتونید ماشینتون رو همونجا بس کنید و معمولا مشکلی اونجا نیست، بخاطر اینکه میتونیم different types of connection available باشه. میتونه 5G باشه، وای فای باشه، خیلی کامیونیکیشن پروتکل‌ها ها هست که ما میتونیم استفاده کنیم. ولی همینطور که گفتم مسئله اصلی تو داینامیک کلاود به وجود میاد که البته سوال خیلی خوبیه. من روی این فوکس نکردم که ببینم دقیقاً سایزش چقدر خواهد بود، ولی خیلی سوال خوبیه.
اوکی، خیلی ممنون. سوال بعدی در مورد همین که حالا گفتین در مورد حالا داینامیک فالت هایی که ممکنه به وجود بیاد، حالا این ماشین بخواد خارج بشه از کلاستر و حالا مثلا فالت به وجود بیاد. حالا روشی که گفتین بر پایه آنالیتیکال مدل بود که حالا اینو مدل می‌کرد و پیش بینی کرد. در واقع دوستان پرسیدن که روش‌های اتو اسکیلینگی که حالا مثلا توی مموری‌های نرم افزاری وجود داره برای همین هندل کردن فالت ها اینجا چقدر میتونه استفاده بشه و آیا اینجا کاربرد داره اونقدر یا خیر؟ مثلا اگر یک حالا ماشین خارج شد بتونه اسکیل کنه و حالا رپلیکیت کنه مثلا اون دیتایی که داره رو مثلا روی ماشین دیگه که کامپیوتینگ اون ادامه بده مثلا.
درسته. خب خیلی روش‌ها میشه اپلای کرد، چون این چیزا تو کامپیوتر ساینس خیلی وقتی که این مشکلات هستن، ولی به خاطر این نیچری که Vehicular Cloud داره یکم سخته، مخصوصا به خاطر اینکه سرعت کانکشن که جوین بشه و اینکه دپارت کنه خیلی کوتاهه، مخصوصا اگه توی هایوی باشه سرعت بالا، ممکنه اون زمان کافی رو نداشته باشه که بتونه این کارو بکنه. ولی یه بحث دیگه که الان خیلی مطرحه، سرورلس فانکشن ها هستن که یه کاری میکنن که دیتا سیو نشه اون توی کلاینت سایت، فقط سرویس ارائه بشه، که این هم میشه اپلای کرد تو Vehicular Cloud. ولی خاطر این چالنجی که هست که خیلی کانکشن خیلی زود ممکنه قطع بشه، این هنوز فکر نکنم بشه اپلای کرد، حداقل at this point.
یه سری سوال در مورد پرفورمنس داستانم پرسیده بودن که حالا این فالت تالرنسی که ما داریم هندل میکنیم آیا اوورهدش مثلا چقدر هست؟ اوورهدش واسه پرفورمنس کل سیستم مثلا قابل چشم پوشیه، یا مثلا بعضی موارد ممکن حتی باعث دیگریدیشن خیلی زیادی واسه پرفورمنس هم داشته باشه؟
درسته، این سوال خیلی خوبیه. ما یه بحثی داریم به عنوان sensitive computation. بسته به این که کامپیوتیشن شما چقدر سنسیتیو باشه، ممکنه بعضی از کامپیوتیشن ها بتونن اینو قبول کنن. مثلا let's talk about like airline navigation system. اینا نمیتونن tolerate کنن هیچ نوع فیلیر، بخاطر اینکه تصمیماتشون خیلی تصمیمات حساسیه. ولی بعضی از اپلیکیشن ها این کارو میتونن بکنن، میتونن tolerate کنن و در اون مواقع میتونیم از ریداندنسی پایین استفاده کنیم، فقط 2 تا نود استفاده کنیم. ولی جایی که واقعا کامپیوتیشن سنسیتیوه، اونجا رو باید دیگه سکریفایس کنی، باید ریسورس ها رو سکریفایس کنی که البته پرفورمنس میاد پایین به خاطر همون. ولی دیگه این یه ترید آف، بستگی به اینکه واقعا چی بیشتر مهمه تو موقع، یا ریسورس یوتیلیزیشن مهمه یا اینکه پرفورمنس. یه بحث دیگه هم که ما انجام دادیم completion time که یه جورایی وصل میشه به همین پرفورمنس، که نشون میده که چقدر طول میکشه که یک جاب کامپلیت بشه، بسته به اینکه تعداد ریداندنسی چقدر باشه. این هم تاثیر میذاره که اونم خودش یه بحث کاملیه که حالا اگه علاقه‌مند بودن میتونم این پیپرها رو باشون اشتراک بذارم. ولی این هم بحثایی که باید کاملا روش بحث شده به قول معروف.
خیلی ممنون. حالا در ادامه این چیزی که گفتین که حالا مثلا بعضی سیستم‌ها خیلی نیاز نیست اونقدر پرفورمنس، ولی در عوض مثلا حالا ددلاین ها مهمه و این داستان ها، توی سیستم ریل تایم چقدر مثلا میتونه استفاده بشه اون جایی که مثلا ددلاین اون خیلی مهمه و حالا مثلا پرفورمنس خیلی مهم نیستش، ولی خب در عوض تضمینی می‌خوایم که مثلا هست که اون اگه هارد ددلاین باشن الزام بخوایم به ددلاینشون برسن، آیا میشه اونجا همین تضمین رو داد با این روش یا نه؟
درسته، اینو واسه داینامیک کلاود بررسی کردن. یه سری از نویگیشن دیسیژن ها هست که کامپیوتیشن خیلی قوی میخواد. بعضی از ماشین ها این چیزا رو ندارن، خاطر اینکه هر ماشینی مختلف و طبق مدلش ممکنه کانفیگوریشنش مختلف باشه، دیوایسش ممکنه پاورفول نباشه. به خاطر همین ما رود ساید اینفراستراکچر داریم که میتونه که ماشین رو کمک کنه. الان یه بحثی دیگه که اومده، همین ریل تایمی که گفتید، اگه تو یه نود adjacent داری تو کلاستر و این نود کامپیوتیشن کامپیوتیشن ریسورس داره که اویلیبله، تو میتونی از اون ریل تایم استفاده کنی، اون دیتایی که اونا قبلا پروسس کردن واسه نویگیشن به تو بدن که بتونی بدونی که قسمت بعدی جاده چه خبره، چجوری تصمیم بگیری. اینو در بحث انتقال داده میشه انجام داد، چون میتونه ترانسمیشن ریتش بالا باشه. ولی اینکه یه چیزی رو از پایه بخوای کامپیوت کنی، از نود بغلیت بخوای، اونو فعلا نمیشه انجام داد، به خاطر همین دیلی که ایجاد میکنه.
خب خیلی ممنون. این سوالی که بچه‌ها پرسیدن تقریبا تموم شده. حالا اگه کسی از دوستان مایل هستش که به صورت وایسی هم سوال بپرسه، میتونه دستشو بالا بگیره که حالا سوالش بپرسه. حالا چند ثانیه صبر می‌کنیم، اگر حالا کسی مایل بود دستشو بالا بگیره، اگر نه که فکر کنم
اگه
سوالاشون
خواستن
رو همه
میتونن
دوستان پرسیده بودن.
اوکی.
بله
اگه
بله
خواستن
بفرمایید.
میتونن با منم تماس بگیرن. ایمیلم توی پاورپوینت
بله
بود، فکر کنم شما هم ایمیل منو دارید، میتونن ریچ اوت کنن. خوشحال میشم
بله
که اگه کمکی از دستم برگیرد.
بله خیلی ممنون. حالا ایمیل و حالا اون اطلاعاتی که قرار در اختیار شرکت کننده قرار بگیرن در اختیارشون قرار میگیره. اگر مایل بودن حالا میتونن به صورت آفلاین حالا بحث رو ادامه بدن با هر کدوم از شرکت ارائه دهنده در واقع. خب خیلی ممنون دکتر از اینکه حضور داشتین در WSS 9 و افتخار دادین تشریف آوردین. از همه حضاری که شرکت داشتن تو این ارائه هم تشکر میکنم و
منم خیلی
تا
متشکرم از
ارائه
شما
ساعت 6
که این فرصت رو پیش آوردین. امیدوارم که استفاده کرده باشم.
خیلی ممنون از شما. متشکرم. خیلی خدا.